Let's wait for a couple of minutes, then I will start. Okay, let's start. Good evening. This is the week 6, the problem solving session for the course Introduction to Atmospheric and Space Sciences. In this course, or today in this problem solving session, we will go through about the assignment questions of the week 6 and the formula for the dew point, several questions related to that, and what is noctilucent clouds, then dew, then fog formations, different types of fog, we will discuss that. After that we will discuss some concepts related to that and some nucleation things, then about the stability, although I have discussed in the previous problem solving session, but in this session also I will discuss. And some numericals on this and ultimately a relation between unsaturated and dry adiabatic lapse rate, the Cape and the Cine derivations, and some precipitation forms. Okay. Before starting, let's go to the assignment questions first. In the week 6, assignment 6, the first question uh, was that the vertically developed clouds are known as what? There are four options: the stratus clouds, cirrus clouds, cumulonimbus clouds, and nimbus clouds. Now, other three, except for the cumulonimbus clouds, are not the developing clouds. Stratus clouds are low level clouds, cirrus clouds are high level clouds, nimbus clouds are also in the lower levels. The only thing which remains, which is the cumulonimbus clouds, which we call as the thunder clouds, they develop from the low level to the top of the atmosphere. Okay, so the right answer of this particular question is cumulonimbus. Let me switch off the video because of the internet issue. Okay. Okay. The second question is which of the following way is or are helpful in convection of air? We have discussed in the previous session what are the different types of convective processes. So the first thing is the surface heating, which is given here, which is, of course, it is a convective process. Through thermals, it rises due to its own buoyancy because the density is less for a hot air, and it goes up and ultimately condenses and forms clouds. Therefore, this is a correct option for the convection of the air. The second option which is given here is the convergence at the surface. Of course, if there is a low pressure system, winds will converge over this low pressure area and the winds cannot go downwards, so it will go upward and result into some kind of cloud formation. And therefore, this is one of the options. This option is correct. The third thing is the topographic lifting. Topography means some elevation like some orography. Therefore, you can find that orographic lifting is also a process of convection. Therefore, the correct option here will be all of these. This also I have mentioned in the previous session. That is, the typical size of the raindrop in micrometer is about 2000 micrometer. 120 to 100 micrometer is typically of a cloud size, and 2 micron and below that, these are cloud condensation nuclei sizes. Okay, so 2000 micrometer is the correct option. Fourth question is, the raising air parcel cools down because the parcel, first option is given that transfer its energy with the surroundings, no possibility of this, due to work done at the expense of internal energy, which is the correct option. Expansion of volume is partially correct, but because of which the temperature decreases is that due to the work done. Therefore, let me go to this. I have shown in the previous session also that how the parcel moves is that if this is the surface and a parcel starts its journey from here, so as it moves up, its volume increases. Why the volume increases? Because according to the parcel theory, the parcel's pressure here should be equal to the pressure outside. In order to balance the pressure of the outside environment within the parcel, the volume has to go up because pressure decreases as we go up in the environment. But in the parcel, therefore the volume must increase. So as the volume is increasing, what happens? Work is done by losing the internal energy to increase the volume. This extra work which is done is resulting in is due to loss of internal energy. And internal energy, as you know, is proportional to the temperature, and hence the temperature decreases. Therefore, the parcel's temperature as it goes up cools down because loss of internal energy. Using that internal energy, some work is done, and because of which the volume increases. That is the simple theory. Okay. Therefore, the right answer for the fourth is due to the work done at the expense of internal energy. Fifth question is, for a stable atmosphere, the lapse rate of the air parcel is dash than the lapse rate of the environment. As we have discussed earlier also in the previous session also, in fact today also I will discuss the same thing, kind of similar things, little more more derivative kind of things. So for a stable atmosphere, we have seen already that gamma of the parcel should be greater than the gamma of the environment. Why this condition is required? This condition is required because gamma p is the lapse rate of the parcel. What is lapse rate? Rate of decrement of temperature of the parcel. Now, if parcel's temperature at a particular height, if gamma p is greater than gamma e, then parcel's temperature at same height will be less than the parcel's temperature of the environment. Sorry, the environment's temperature. Therefore, temperature of the parcel will be less than temperature of the environment. This condition will give this. As a result, what happens? Parcel will be more dense or more denser. So it will be, parcel will be denser than the environment. And as a result, this parcel will fall. And this is the stability condition. Therefore, for a stable atmosphere, lapse rate of the air parcel is more than the lapse rate of the environment. Sixth question is, when an air parcel rises, then its temperature and internal energy. The first option is that temperature decreases, internal energy increases. It cannot be possible. Why? Because internal energy is related to temperature, particularly internal kinetic energy. Therefore, it cannot be possible. Second option, temperature and internal energy both decreases, which is true. Temperature increases, internal energy decreases. Again, it cannot be possible. And temperature decreases, internal energy remains constant. No, this is not true. As I have already mentioned the process, what happens when the parcel goes up. Therefore, the correct option will be temperature and internal energy both decreases. Seventh question is, an air parcel is said to be unsaturated if relative humidity is. Two words, one is the unsaturated. Unsaturated means that actual vapor pressure, let me go to that. See, relative humidity is E by Es. What is E? The actual vapor pressure. What is Es? The saturation vapor pressure. When we call the parcel is saturated, when E becomes equal to Es or relative humidity becomes equal to 100%. Then only we term the parcel to be saturated. But for unsaturated process, this actual vapor pressure will not be equal to Es, or I would rather say E will be less than Es. Therefore, relative humidity will be less than 100%. That should be the condition. Okay. Therefore, an air parcel is said to be unsaturated if the relative humidity is less than 100%. Simple. Eighth question represents the moist adiabatic lapse rate is less than the dry adiabatic lapse rate due to what? The moist adiabatic lapse rate is less than dry adiabatic lapse rate. Any lapse rate, any lapse rate is less than the other means what? That particular parcel will have higher temperature than that of the other. Therefore, gamma of the moist parcel is less than gamma of the dry parcel because of it consists of moisture. And moisture, when condenses, gives latent heat. And this is the only reason why moist parcel is warmer, and hence gamma m is small. Therefore, the option will be latent heat. Ninth question represents clouds which form at highest altitude are known as cirrus cloud. As I've already shown you the entire picture of the clouds in the previous session, it will be easier for you to guess that what will be the actual answer, because cumulus clouds is a lower level cloud but developing clouds, and that develops into cumulonimbus. Cirrus clouds are the only clouds which are at the top, very fine thread-like structure. Stratus clouds, the lower level clouds, and nimbus clouds are the rain-bearing clouds, which happens to be at the lower level. Therefore, the correct option here is cirrus, which is formed at a higher altitudes. 10th question is, which of the following clouds cause heavy rain? Cirrus cannot cause heavy rain because, as if you see the problem solving session, 5th problem solving session, the last one, its picture, then you can see that it's a very high altitude cloud and very small thread like structure is there, so it cannot cause heavy rain. Then stratus, no, it's a fog like structure, it does not rain much. Cumulus is small, some cauliflower shaped clouds, that also does not rain much as compared to cumulonimbus. As you have seen that in the previous session, that cumulonimbus looks like this, kind of this. It starts from the lower level and it reaches like this at the top. So these are thunder clouds, so these rains much more. Therefore, cumulonimbus leads to heavy rain. Okay. So here the option is cumulonimbus. 11th question is, the ratio of the moist adiabatic lapse rate and dry adiabatic lapse rate is. See, moist adiabatic lapse rate, we generally consider it as, actually this is kind of a saturated, so it is about 6 degrees Celsius per kilometer, and gamma D we have derived, it's about 9.8, we roughly take it as 10 degrees Celsius per kilometer. Therefore, the gamma m by gamma D, if you do, it will be about 6 by 10, that is 0.6. Therefore, 0.6 is the right answer. 12th and the last question of the assignment is, in the nomenclature of the clouds, the term nimbus is added to indicate. I have I have already said in the previous session, nimbus means rain bearing. So precipitation is the correct option. Therefore, we have discussed all the 12 questions of the assignment of the week 6. These are easier questions, whatever I have given in the last problem solving session. Based on this, I hope you have done it. Okay. Now, we will proceed towards the dew point. which I have uh, already explained in the last class. I have explained the dew point process, that process in which an unsaturated air parcel, when isobarically cooled, so I will write it here, unsaturated air parcel is cooled isobarically at constant pressure, and of course it is a parcel, so it is adiabatically also. It leads to saturation at a temperature. That temperature is known as the dew point. Now here what I will do is that I will introduce a formula for the dew point. For that, I will just start with the concept of the relative humidity. What is relative humidity? RH. Relative humidity is actual vapor pressure divided by saturation vapor pressure, or actual mixing ratio divided by the saturation mixing ratio. I am representing W with mixing ratio. People represent R with mixing ratio also. Okay. Now, relative humidity becomes 100% or equal to 1. If we multiply by 100%, then it will be in percentage. Should be equal to E by ES or W by WS. That means when the dew point is reached, let me write here, when dew point is reached, W will be equal to WS. Initially, if a parcel has some mixing ratio W, then if we isobarically and adiabatically cool it, then this same W will become WS at a temperature T, which is called the dew point temperature. Therefore, I will use the formula of WS, and we know what is WS. It is epsilon ES by P. P is the total pressure, ES is the saturation vapor pressure, and epsilon is 0.622. Okay. Now, at dew point, W will be equal to WS, fine, and also E is equal to ES, whatever, fine. Now, apply Clausius-Clapeyron equation. What does it say? ES, which is the function of temperature, is A e to the power minus B by T. Now here T will be equal to TD, because we are assuming that dew point is reached now. Parcel is saturated now. Therefore, we are writing this W is equal to WS or E is equal to ES. Okay. Therefore, E or ES you can write at TD will be equal to A e to the power minus B by TD. Now W, as per the formula, epsilon A e to the power minus B by TD divided by P. Right? This should be the formula. Now what I need this dew point temperature, because I need the formula of this dew point. Therefore, I multiply here PW divided by epsilon A. Okay, that will be e to the power minus B by TD. Now I come here. Okay. Now take log on both sides. Therefore, we have log PW divided by epsilon A will be equal to minus B by TD. Therefore, TD will be equal to minus B divided by log of PW by epsilon A. Or the final expression is you take the negative sign inside the log, how we can write it? It will be epsilon A upon PW. This is the expression for the dew point temperature. Okay, this is the expression for the dew point temperature, which depends on this constant B, which is known. Okay, let me write it here in a short box. A is actually 2.53 into 10 to the power 11 pascals, and B is 5420 per Kelvin. Kelvin. Okay. Therefore, B is 5420 known, epsilon 0.622 known, A is also known 2.53 into 10 to the power 11. P is the pressure level at which the parcel is present, because I am doing an isobaric process. Therefore, P must remain constant. Therefore, P will be fixed for the parcel. What about W? W is the mixing ratio initially the parcel is carrying, because I am not adding any moisture. In case of wet bulb, we have added some moisture, but here we are not adding. Therefore, W is not changing. Therefore, that temperature Td at which W becomes Ws, at that temperature, it is called the dew point process, or the dew point is reached, where relative humidity becomes 100% or equal to 1. This is an extra thing, but is a very important thing to understand. So this is the formula for the dew point temperature. Now, based on this formula for the dew point temperature, I have done some given some questions here that will help to understand this particular concept. Okay. The question here given is, what is the dew point temperature of a parcel at surface with dry bulb temperature 20 degrees Celsius, and this surface is represented by 1000 hectopascals. Okay. Now, see what all things are given. Given the temperature, the actual temperature, the dry bulb temperature, that is 20 degrees Celsius or 293 Kelvin. Right? This is given. The pressure is also given, that is 1000 hectopascals. But what is not given is dew point temperature, which we need to find. Therefore, we write to find T dew point. And we know the formula. What is that? Td will be equal to B upon log of epsilon A upon Wp. Only thing which is left to find is W. Okay. Now what I will do is that I will find out the saturation mixing ratio. For that, what I do is use Clausius-Clapeyron equation. Let's write them. Es will be equal to A e to the power minus B by Td. Let's calculate. Will be 2.53 into 10 to the power 11 e to the power minus 5420 divided by 293. And that comes out to be about 23.41 millibar. Fine. Now from here we can calculate the saturation mixing ratio, and that will be equal to epsilon Es by P, that is 0.622 into 23.41 divided by P, that is 1000, and its value comes out to be about 0.0145. and that is equal to W for dew point. Okay. Now I write TD will be equal to 5420 divided by log of epsilon A, therefore 0.622 into 2.53 into 10 to the power 11 divided by 0.0145 into 1000. But we cannot write here 1000 because all things are in SI units. Therefore, we have to change it in pascals. Now, as we calculate all those things, it comes out to be about 292.9 Kelvin. And it's nearly about 19.9 degrees Celsius. Now, why is it that it is very close to 20 degrees Celsius? This is because we have assumed here that Ws or Es at this temperature, T, dry bulb, this temperature, the saturation is already assumed to be that equal to W because no other information is given. Therefore, our mixing ratio, actual mixing ratio the parcel is having is actually this. Therefore, at dew point temperature only we are calculating this particular thing. Therefore, this dry bulb temperature has already become dew point temperature at 20 degrees Celsius because of some cooling, isobaric cooling. And hence we are getting a dew point temperature which is equal to, nearly equal to the dry bulb temperature. This question will be much more clearer. Question is, what is the mixing ratio of the parcel at 900 hectopascals if the dew point temperature is 13 degrees Celsius? Well, here now mixing ratio has to be calculated, and at 900 hectopascals the dew point temperature is given. Therefore, given the dew point temperature which is 13 degrees Celsius or which is equal to 286 Kelvin. Now pressure is 900 pascals. Mixing ratio W we need to find out, and I know the formula, that is TD is equal B by log of epsilon A upon WP. I need W. Therefore, what I will do is that I will take this on the other side and it will be B by TD. Take the exponential on both sides, we get epsilon A upon WP e to the power B by TD. Right? Now W is required, I take it in this side, therefore it will be epsilon A by P e to the power minus B by TD. Now just put it and get the result. Epsilon is 0.622, this is 2.53 into 10 to the power 11, e to the power minus 5420 divided by 286 divided by 900. What is W? Let's calculate. It's coming around 0.010. What does this mean? At 900 hectopascals, at dew point temperature, 10 grams of water vapor is present in 1 kg of dry air. And this W is nothing but the saturation at 13 degrees Celsius. At 13 degrees Celsius. In the previous question, nothing about the mixing ratio is given. Therefore, we have assumed this thing. As no info about W, therefore we assume that this ES is, I mean, this is the saturation vapor pressure at 20 degrees Celsius is whatever, we get the saturation mixing ratio, and that is nothing but the actual mixing ratio. That means that really means that actual mixing ratio has already become saturation mixing ratio at 20 degrees Celsius. And if that is true, then this dry bulb temperature, if 20 degrees Celsius, means the dew point is also 20 degrees Celsius. It should come, and it has come about 19.9 degrees Celsius, that is 20 degrees Celsius. Okay. So this is the concept of the dew point. Okay. Now this is a slide, just a minute. This is a slide about the noctilucent clouds, which are the very high level clouds. These are not the clouds which typically represent any weather phenomena in the troposphere. It's not in the troposphere, first of all. In troposphere, whatever the clouds are present, I have already shown in the previous session. That is starting from the cirrus clouds, cirrus, alto related clouds, then cumulus clouds, then stratus clouds, and in fact cumulonimbus. These all clouds are in the troposphere. Okay, but these noctilucent clouds are not present in the troposphere. So where is it present? It is present about at a height of 76 to 86 kilometers. 76 to 86 kilometer means it is near mesosphere. These clouds are generally seen at north 50 to 70 degrees north during the twilight, and it generally consists of water and ice only. Fine, but these kinds of clouds generally represents the atmospheric means if these noctilucent clouds can represent how the atmosphere is changing in a very upper atmosphere. Fine, this is the small and brief information about the noctilucent clouds. Next is the process, which is called the dew. Now we have seen already that dew formation takes place when there is a clear sky, somewhat cooler atmosphere. On the grass tips, in fact in the cricket matches also, we have seen that dew plays an important role. So what is this dew? How these dews are formed? This process I will discuss here in a very short and brief way. What happens is that in a clear sky during winters, during winters, when clear sky is present and lower surface have some moisture, three things. One is during the winters it should be cooled and clear sky should be present. This is the second condition. Third condition is that the lower surface some moisture must be present. Then what happens is that if this region is cooler, and during the night time, during night, why during night? Because at night the solar radiation is completely cut off, as a result of which the infrared radiation starts emitting. the heat is lost. As the heat is lost, this surface becomes extremely cooler. Surface cools. And as the surface cools, over the tiny tips of grasses, or the tips of grasses, or the leaves, at the tips of leaves, or over the cars, you can find out some dew drops. And these grass tips or the tips of the leaves or over the car some dust particles which are present, this acts as condensation nuclei. Okay, and over these condensation nuclei these dew drops are formed. Therefore there are several conditions which are there. One is during the winters, already the atmosphere is cold. During the night time, and it should be clear sky, no infrared radiation blockage should be there. If these kinds of conditions are present and the surface has some kind of moisture, then over the tiny tips of grasses or over the tips of leaves or over some dust particles over some cars or anything, or window pane even, you can find out some condensation droplets to form, and that is nothing but the dew. And in fact, I will discuss about the fog. Same kind of atmosphere is required, but fog occurs somewhat at a from surface to some greater levels, and it those particles, those water droplets, they tends to suspend there in the air like clouds, but low level clouds. That is nothing but fog. I will discuss. So this is the concept of dew. Okay, this is now the fog. Fogs are nothing but the clouds formed at the lower level of the ground, as I have already discussed. And particularly the type of fog which we see generally is the radiation fog. How this radiation fog is formed is quite related to that of the dew process, which I have already, dew formation process, which I have already told. But this I will explain. These all four things I will explain. What happens is that in the particularly in the northern Indian region, you will find fog during the winters, particularly during the December, January. Why this forms? This is because, see, for fog formation you need some moisture. In the northern India, where from this moisture they get this moisture? This moisture comes due to a phenomena called western disturbances. These western disturbances are cyclonic circulations. It gives, it gives some rain over northern India. And this, after this rain period, absolute calm winds are seen. And these calm winds and clearer sky result into formation of these fogs. And after some period of fog also, some cold advection comes, cold advection. That actually releases the fog. Okay. Now these four types of fogs I will discuss one by one. Okay, the first type of fog is the radiation fog. It is quite similar to the process as I have already mentioned about the dew formation. Okay. Radiation fog. Again, winter night. Conditions, let us list it down. Winter night, number 2. Clear sky. Number 3, calm winds, and number 4, low level moisture should be present. If these 4 conditions satisfies, then this kind of fog you can see. And most of the times in the northern India, whatever fog we see is actually this radiation fog. This is a surface, and suppose the moisture is present up to some levels, some particular level, the moisture is present. Absolute calm wind condition is present. No winds are blowing, less than 5 knots. Knots is a unit of wind. So winds are less. Okay, and at that time it is a clear sky. No clouds are present. Therefore, the infrared radiation is lost very easily. As the infrared radiation, as you know, that it is related to the heat. As it is lost, this heat is lost from the surface, and as a result of which this entire surface and up to some level it cools down. This layer absolutely cools rapidly, and as the temperature drops down, you can find out that over some dust particles, this moisture tends to condense and they remains suspended in the air, and as a result of a deep fog formation takes place. This is the radiation fog. The second type is known as the advection fog. Now what happens is this in this advection fog, as you can see the term advection means horizontal movement of winds. This is horizontal movement. One, we have seen the convection, which is the vertical movement, and this is the horizontal movement of some moisture or something like that. Okay. Now what happens is that suppose there is a cooler region is present over here. This is cooler region. Okay, now I will change the color. Now we have already studied about the fronts. What is fronts? Between two air masses, suppose this is warm air mass and there is a cold air mass. Between these two, a front formation takes place based on depends on the speed of the air mass. Whichever is dominating, that will be the direction of the front. If warm air mass, and this is the cold air mass, if warm air mass has higher speed, then the front which is formed is the warm front, because it will go towards the direction of the warm air mass. Now here, if a warm air mass which consists of more moisture, therefore warm and moist air mass, if it gets advected towards this colder region, what happens? This cooler region will takes up the heat and this becomes cooler, and as a result of which you can find out some fog formation over this region, and it is remaining suspended over some condensation nuclei. Definitely condensation occurs only over some particular nuclei, therefore these nuclei should be present here, and this cooler region actually cooling this particular warm air mass, and as a result of which, and it already consists of moist air, and as a result of which the condensation is taking place and fog formation takes place. This is the second type of a fog. Okay. Now the third type of a fog is upslope fog. It is quite similar to that of the orographic ascent kind of thing. Upslope fog. Of course, this mountainous region should be present, as I am telling the upslope. Very little speed of the winds, not very strong winds, as we have seen in the case of convection. Strong winds is not present. Very calm, cool winds, which is moving slightly upward, warm and moist. So as it moves upward, it cools down, because the pressure decreases. As we move upward, the pressure decreases, and again this volume increment and internal energy lost, and hence the temperature decreases. As the temperature decreases, condensation may start, and since the condition is not very strong windy condition, calm, although less wind speed is there, here some kind of fog formation takes place. Some condensation you can see, not clouds but fog. And the fourth thing is that the evaporation fog. These are the four basic types of fog. There are many other classification, but I'm not going into that details. The last one is the evaporation fog. What is evaporation fog? We all have done this same thing during the winter time. When you open your mouth and talk, you can see that some smoke kind of things is coming from your mouth. This is because your mouth is warm as well as moist, and so when you talk, some moisture or some vapors are coming out, and since the outside region is cold, as a result of which some kind of fog formation takes place. Okay, it's quite similar to that of the advection kind of fog, but here what happens is that you have a warm ocean kind of thing. The best example which I have given already, this is suppose a warm ocean over very less windy, calm winds are coming, which are cooler. Over this region it is cooler. Then what happens? Again, this region you can find out fog is formed. This is known as the evaporation fog. Okay, so there are four types of fogs. I have explained one by one. Okay, now I am always saying that warm and moist air. Why warm air consists of more moisture? This is the question which I will try to answer. This is the question, that why does warm air holds more moisture? Okay, warm air holds more moisture. What is the reason behind that? Now you consider a container. Consider a container where you have large number of condensation nuclei. Now, since the temperature here is very warm, okay, this is warm and this is suppose the cold condition, and these are the condensation nuclei. Say this is the nuclei. Condensation. Okay, and this is T cold. Now, in this warm temperature beaker, what happens is that as the temperature is warm, the kinetic energy is high, right? Kinetic energy is high. Now, if the kinetic energy is high, then these molecules or these condensation nuclei tend to move very faster, and it collides each other and moves faster. And as it moves faster, it is difficult for the vapor molecule to condense on this particular nuclei. So it is difficult for vapor molecules to condense on these fast moving nuclei. Hence, vapors remains. That's why we say that warm air consists of more vapors or more moisture. But in case of this cooler region, cooler temperature, not much movement in the condensation nuclei can be seen because the temperature is cold. Therefore, this it is easier for vapor molecules to stick to the condensation nuclei. As they are moving slowly. Now, if these vapors get condensed, then less vapors, so less moisture. This is the reason why we say that warm air can hold more moisture as compared to that. It's not just holding, it's easy to understand in this way. Okay. Now another short topic. What is homogeneous and heterogeneous nucleation? Now, as the term is nucleation, it is related to the condensation nuclei, but there are several nuclei. I will divide it into two parts. One is hygroscopic, another is non-hygroscopic. Hygro means water. Okay. Now this is have some water affinity. It attracts the water. But this is water repellent. Okay. This example is wax, paraffin. These are examples. You can find out many more. And the most important example of hygroscopic is salt. Sea salts, you can say. These are all hygroscopic nuclei, and these have an affinity towards the water. Now what happens is that in heterogeneous nucleation, because of this hygroscopic nuclei, let me write first, heterogeneous nucleation. Here condensation process starts even before the relative humidity have reached 100%. So even before relative humidity have reached 100%, condensation process starts. Why? Because these salts or these hygroscopic condensation nuclei, they have a tendency to attract the water. Okay, affinity towards the water. Before the relative humidity have reached 100%, this nucleation takes place, and this nucleus, particularly the hygroscopic nucleus, they tend to result in condensation. But homogeneous nucleation, it's particularly due to the non-hygroscopic. What happens in this homogeneous nucleation process? Condensation process does not start even when the air is supersaturated. What is supersaturation? More than relative humidity, more than 100%. Supersaturated. Let me write it again, just a minute. Even when the air is super saturated. This, what is the meaning of supersaturation? Relative humidity greater than 100%. So even when it has reached some 100.9% relative humidity with 0.9 supersaturation, you cannot still find condensation process to occur because of this kind of non-hygroscopic nuclei. So this is the process of homogeneous and heterogeneous nucleation. Now, so far we have seen that homogeneous nucleation and heterogeneous nucleation. We have seen why does warm air holds more moisture, fog types, upslope fog, evaporation fog, advection fog, and radiation fog. What is the process of fog? What is actually fog? Then we have seen about the dew, how these dews are formed, noctilucent clouds, very small description about the noctilucent clouds, and we have seen the dew point formulation, and we have discussed the assignment questions so far. Okay, now we will go towards the concept of stability again. I have already explained some concept of stability, but I will again explain the concept again. That will be more clear and more elaborative way I will try to explain. Okay. Just a minute, I will just. Okay, in stability, what we will do is that we will consider first, or let us say assume. We will assume that environment, two things are there. One is the parcel, another is the environment. This is parcel, another is the environment. Okay, so now environment will be in hydrostatic balance. This is the first assumption which we will take, that environment will be in the hydrostatic balance. What is that means? That dp dz should be equal to minus rho g, rho eg. Why rho e? Rho e corresponds to the environment. Let us write it then. This is parcel and this is environment. Okay, so this is T. Let us write the virtual temperature. The virtual temperature of the parcel. Let us write the virtual temperature of the environment. Because why we are writing the virtual temperature? Because ideal gas equation for moist air, or moist, I would say unsaturated air, but moist air, let us write the Pm into alpha m. I am writing in terms of specific volume, therefore it should be either Rm into T, or it should be written as Rd into Tv. I am taking this consideration where Rd, the dry specific gas constant I am using. For that I am using the virtual temperature, or else you can use this Rm and take the dry bulb temperature. Anything can be possible. We have seen it in the very earlier lectures. Okay, so for parcel I am taking this condition, the second one, parcel TVP, the virtual temperature of the parcel, virtual temperature of the environment. The immediate next thing is the rho, the density of the parcel, density of the environment, which I have written here. Okay. And what else? I think that's all. That is all we require. Fine. Now let us consider a parcel, and let the reference be z is equal to 0, and let us consider that it will move some delta z distance. Okay, why? Because there is a gravity which is acting downwards. There is a buoyancy due to the environment to the parcel upward. Therefore here if we apply the Newton's laws of motion, the second law of motion, then we can write it that rho, okay, rho parcel into volume, if this is the volume of the parcel, into delta z. See, rho p into v is nothing but the mass of the parcel. The parcel's mass into acceleration delta z double dot will be equal to buoyancy rho e minus rho p into v into g. That is fb minus g. That's all. And I am using the mass also, so that's why we are writing like this. This is the buoyancy. Now what is happening is that delta z double dot is positive in terms of in the direction of the buoyancy force, and buoyancy force is due to the environment only. That's why rho e vg I have taken first, then parcel rho e minus rho p. That's why I have written. Now vv you can chop out. I will then write delta z double dot will be equal to rho e minus rho p divided by g. Oh no, g divided by rho p. Okay, this is the expression which we are getting, and I have already shown that this is the expression in the last class. Okay, now from here what we can see and whatever we can analyze is that, number one, if rho e, that is environment's density, if it is greater than the parcel's density, what should happen? What should happen? If environment's density is higher than the parcel, then parcel will go up. Is it happening here? See, rho e, if it is greater than rho p, this becomes positive, so acceleration is positive, and I have taken the z direction positive in the upward direction, therefore it will move up. That is true. Okay, therefore we can write delta z double dot is greater than 0. Acceleration is positive. Number 2, if rho e is equal to rho p, what will happen? If rho e is equal to rho p, then delta z double dot will be 0. Nothing is going to happen because all are at the same density. Third thing is, if rho e is less than rho p, then what will happen? Delta z double dot will be less than 0. Some decelerating case, or it is parcel will resist to stay at its own location or can move somewhat downward. Okay, this is the thing which we can see from this. Let it be 1. Fine. Now we will derive much further. Okay, I'm starting from this top. Now delta z double dot from 1. Okay, delta z double dot can be written as, see, we have rho e minus rho p. This rho e, let us write it first. Rho e minus rho p by rho p into g. This is the thing, right? Now rho e can be written as what? P divided by Rd into TVE minus P divided by Rd into TVP, okay, into G divided by P divided by Rd into TVP. Right? Now why P's are same? Although the parcel is there and an environment is there, why the pressure is same? This is because the parcel and the environment at a particular level, they must be at same pressure. This is the assumption which we are taking from the very starting. Therefore this P must be same. Okay, now this P you can chop out, and ultimately the expression will become like this. Delta z double dot will be equal to TVP minus TVE divided by TVE into G. Right? This will be the expression. Now you consider a parcel at z is equal to 0. Now here the temperature TVE of 0 and this TVP of 0, they must be same because the parcel is originated from the 0 level only, and therefore the temperature should be same as that of the environment at the 0th level. Now at some higher level, TVP can be written as TVP0 plus delta TVP by delta Z into delta Z. Similarly, TVE can also be written like this, plus delta TVP, E by delta Z into delta Z. I just substitute these two in this. What I get is delta Z double dot will be equal to delta TVP by delta Z minus delta TVE by delta Z into G delta Z divided by, let us keep it like this, right? Now what is this? Delta TVP by delta Z. This is nothing but the lapse rate, negative of that. These are lapse rates of respective systems. Okay, therefore delta Z double dot, I can write this as what? Minus gamma P. This can be written as gamma E divided by TVE into G into delta Z. Right? Now, what I will do is that I will write this same expression as this, minus n square delta Z. So what is this n or n square? N square is gamma P minus gamma E divided by TVE into G. And this n is called Brunt-Väisälä frequency, or you can see it as buoyancy frequency. How to calculate the time period then? The time period will be 1 by n. That's all, as per the definition. Okay. Now, if you see this particular differential equation, what will happen if n square is greater than 0? Then it will be delta Z double dot plus n square delta Z should be equal to 0. What does this mean? A cos nt plus b cos b sin nt. Some kind of oscillation. What will happen is that, suppose this is an equilibrium level where parcel is there. Now, as the parcel starts moving up, because of the temperatures or the buoyancy, this parcel will come down, go slightly back below, and again come back. So this way it starts oscillating and ultimately it will damp out. This is the stable condition. Why it is stable condition? See n square greater than 0 from this expression of n square. N square greater than 0, what does it tell? Gamma P is greater than gamma E. And this we have already discussed that it is a stable condition. Why? Because gamma P, the parcel's temperature, is lower than that of the environment's temperature. Higher means what? Decrement is less. Higher lapse rate means decrement is less, because lapse rate is the decrement of temperature with height. Therefore, higher lapse rate of the parcel as compared to environment, representing that the parcel's temperature is lower as compared to the environment. That's why it cannot move further up. It goes down, it goes further down, but again it has some effect. Again it will go up. Like that way it will oscillate. That's why this oscillatory solution we are getting. Second thing is that if n square is equal to 0, nothing, delta Z will be 0, nothing will be there. Okay. Now, last thing is n square is less than 0. What will happen? We get minus n square delta Z equals 0. That means delta Z will be equal to a e to the power nt plus b e to the power minus nt. Two extremes. Either it will go up from this particular level, or it will go absolutely down from this particular level. This is the condition of unstable atmosphere. Because if you see n square less than 0, then gamma P is less than gamma E. That is, environment now has low temperature as compared to the parcel. This is the unstable condition where the parcel has higher temperature, less dense, and it can move up. Mostly the upward solution is preferred in case of atmosphere, not this one. Okay. So this is the complete picture of the stability. Now, in another way, we can derive we can talk about the stability that is based on the potential temperature. So this potential temperature thing I will discuss, but before that we will do some numericals. Although there are no numericals in the assignment 7, the concept is very important. So this concept will be helpful also. Okay, fine. Let's do this numerical first. Okay, a parcel having lapse rate of 7.5 degrees Celsius per kilometer and the environment lapse rate is 6.5 degrees Celsius per kilometer. Environment temperature is given. The parcel will oscillate or it will move up to a greater heights. Now see, from the given information what we are getting, given information says that parcel's lapse rate gamma p is 7.5 degrees Celsius per kilometer. We have to be very straightforward about this, that lapse rate means rate of decrement of temperature with height. Decrement. So high means at a particular level parcel's temperature is lower as compared to environment. I'm repeating every time. Gamma E is 6.5 degrees Celsius per kilometer. This means what? At a particular level, parcel's temperature is lower than that of the environment. If this is the condition, then what will happen? This situation represents that gamma P is greater than gamma E. That means a stable condition. Right? We have already discussed in the previous session, also in this session. Stable condition. It will oscillate, therefore, which we have seen in this case. Okay, it's a stable condition, it will oscillate. Oscillations can be seen. Sorry. Oscillations can be seen because it is a stable atmosphere. What is the time period of oscillation? What we need to calculate? Just calculate in square, the Brand-Weissel frequency. What is that? Gamma P minus gamma E divided by TVE into G. Consider that this TVE is nothing but this environment temperature. Okay. Now gamma P is 7.5 minus 6.5. Remember, this is in degrees Celsius per kilometer or degree Kelvin per kilometer. But this is kilometer, which is very important. Therefore, we have to multiply it with 10 to the power minus 3. That becomes in meters. And we have in 288 Kelvin. Fine. Now this will be in Kelvin per meter. Okay, this will be Kelvin of this particular thing. Okay, into meter per second square, that is into 9.8. Right? 9.81. Oh, sorry. 9.81. The value of the acceleration due to gravity. Now, if you would do it, you could calculate it. It will be 1 into 10 to the power minus 3 into 9.81 divided by 288. What does the unit comes? Kelvin, meter, 1 per second square. Right? This is n square. So what is n square comes out to be? Let's calculate it. So it's 9.81 into 10 raised to the power minus 3 divided by 288. It comes out to be about 3.4 into 10 to the power minus 5 per second square. Then what is n? This is root of it. It about 5.83 into 10 to the power minus 3 per second. Now we need time period. Now what will be the time period? T, that is equal to 1 by n, that is 1 by 5.83. I am just writing 10 cube in the upward side. 1 divided by answer is about 171.3 seconds. This is the time period of oscillation. Okay, this is a complete stability related question that will help to understand your concept. This is what I was talking about. Okay, this is about the potential temperature and relating it with the stability and the instability. There is a question related to that. Then I will tell you about the unsaturated air parcel and dry adiabatic lapse rate. And then Cape and Cine derivation is a new thing which will be interesting to know. I have given the concept. And then some types of precipitation when it will form. Detailed types of precipitation and how the precipitation is measured with curvature and solute effect, diffusion growth. These things we will see in the next class. But before that, let us complete this particular thing. Okay. Now here the question shows, it's a derivation based question. Show that if the potential temperature increases with increasing altitude, the atmosphere is stable with respect to the displacement of the unsaturated air parcels. Now we have seen the potential temperature. Now what is the potential temperature? As I have already told, the potential temperature is that temperature of the air parcel, or the temperature of the air parcel at a particular pressure level with respect to 1000 millibar. Now if we compress or expand any air parcel and come and put it back to the 1000 hectopascals, whatever the temperature it finally attains is the potential temperature. So 1000 MD is the reference point. Therefore potential temperature, which is theta, we have derived that will be equal to temperature, or you can write it as TV, the virtual temperature, P naught by P to the power RD by CPD. I am writing it D because of this virtual temperature, which we have already taken. Otherwise we have to take RM by CPM, and this CPM I will discuss how to calculate this specific heat capacity for moist air. We have seen for dry air. For vapor, some mistake was there in that particular thing, because vapor is not a diatomic gas. It's a triatomic gas, but it's a peculiar kind of gas. Its degree of freedom is different. But I have taken there as a diatomic gas. That is not true. The actual value I will derive very soon. Fine. So this is the expression of the potential temperature. Now what I will do is that I need what? Potential temperature increases with altitude. Right? If potential temperature increases with altitude, what does this mean? We need delta theta delta z. Simple. Okay. If this is the expression now, I take log of both sides. So log of theta will be equal to log of TV plus RD by CPD log of P naught minus RD by CPD log of P. Okay. Now I differentiate both sides. With respect to Z. You can do it with pressure also, because pressure we have already seen that Z and pressure we have a relation. So we can do it in that way also. But I am writing now in Z because it is altitude directly mentioned. Now let us write 1 by theta d theta dz. That will be 1 by TV dTV by dz plus, this will be 0 because P naught is constant, 1000 millibar. This will be completely 0 if you differentiate. This will be RD by CPD 1 by P dP by dz. Right. Now multiply TV on both sides. Therefore TV by theta d theta dz will be equal to dTV by dz, okay, minus RD by CPD is there, so let us write it, it's fine. This will be 1 by P, it's okay. And this dP dz, using hydrostatic approximation, we can write rho into G, fine. Therefore dTV dz minus, oh, there is a TV, I forgot. Yeah. Now this RdTV by P can be written as specific volume, because P alpha is equal to RdT, or yeah, alpha of moist. So this is CPD, and this minus minus becomes plus, rho into G, and rho and alpha we know that rho is equal to 1 by alpha, therefore it can be chopped out. Now what is this G by CPD? G by CPD is nothing but the dry adiabatic lapse rate, and this is what? Environmental lapse rate. Therefore gamma E, let us write it with a negative sign because there is no negative sign here, but G by CPD is nothing but gamma D, right? Or I can write, if this CPD becomes CP moist, then this will be gamma of some parcel. Therefore we can see that gamma of parcel minus gamma of environment will be equal to TV by theta d theta dz, and this TV you can consider as an environment temperature, okay. Now if d theta dz is greater than 0, if d theta dz, this thing which is to be shown, if d theta dz is greater than 0, then you can see that gamma P is greater than gamma E. What is this condition? Stable, right? This is what it needs to be shown, which we have shown now. Another condition let us take. Second condition, if d theta dz it is less than 0, then what will happen? Gamma P will be less than gamma E. What is that? Unstable condition. And if it is 0, then nothing, gamma P is equal to gamma E, okay. So this d theta dz can also tell us whether the parcel is stable or the atmosphere is stable or not, unstable, right? And based on this also we will do some one numerical. This is the numerical which I have framed. If the potential temperature of the environment is increasing at 2 Kelvin per 100 meter, and at a level the potential temperature of the environment is 27 degrees Celsius, what will be the frequency of the oscillation of a parcel in that environment? I know that n square is what? Let's see it. N square is gamma P minus gamma E divided by TVE into G. Let's write it. Gamma P minus gamma E divided by TVE into G, right? Okay. And this gamma P minus gamma E is nothing but this, right? Just replace it with this. N square will be equal to TV by theta TVE. This will be d theta dz into G. And this TV is actually this TVE only. So TV can be chopped out. Therefore n square can be written as 1 by theta or G by theta d theta by dz. Okay, this is very important. This is another expression of Brand-Weisshaller frequency. Now it is easy to do this particular question. And here only frequency of oscillation is n we need to find out. Fine. Potential of the environment is known. Therefore, theta is already known. That is 27 degrees Celsius. That is 273 plus 27. What is that? 300 Kelvin. You have to convert. Always you have to convert. And if the potential temperature of the environment is increasing, so d theta by dz is 2 Kelvin per 100 meter or 0.02 Kelvin per meter. Just see, as you can see, it is increasing. Therefore, oscillation will be there, right? That's why this question also says that frequency of oscillation, right? It's a stable environment because d theta dz is greater than 0. Just we have seen. Therefore, n square will be equal to 9.81 divided by 300 into 0.02. All are in SI units. Just calculate. Let me calculate just a minute. 0.02 divided by 300. It comes out to be about 6.54 into 10 to the power minus 4 per second square. Therefore, n will be what? Root answer. This will be n 0.0255 per second. This is the frequency of oscillation. Although it is not mentioned in the question, but you can find out the time period of oscillation also. That is 1 by n. Let's do it. It's about 39 seconds. Okay. So 39 seconds is the time period of the oscillation in that stable atmosphere of the parcel. This is what is related to the stability. Now, the relation between unsaturated parcel and the dry adiabatic lapse rate. Okay, fine. See, unsaturated parcel means it consists of moisture plus dry, and this is absolute dry. Okay. Now, for dry adiabatic lapse rate, we have derived that gamma d, the lapse rate, is G by CPD, right? Now, for moist or unsaturated air parcel, I am writing it as gamma m is G by Cp into m. This is okay, let us write it okay, unsaturated air parcel will be this. Now, how to calculate this CPM? How to calculate this particular specific heat capacity at constant pressure for unsaturated air parcel? For that, let us consider that we have 1 kg of dry air and W grams of vapor or W kg of vapor. Let me mention you first. In the fourth week, I have already shown how to find out this Cv for the vapor and Cp for the vapor. But whatever the expression we have got is wrong because we have assumed they are a diatomic gas. Okay, but water vapor is a triatomic gas, right? But its degrees of freedom, because we have seen the law of equipartition of energy through which we are deriving. So degrees of freedom for water vapor is 6. It's not 7 like other triatomic gases. So it has 3 translation plus 3 rotation. So it is a kind of a peculiar kind of gas which has 6 degrees of freedom. You have to remember this. Therefore, CVV will be equal to how much? It will be just degrees of freedom divided by 2 RV. Therefore, 6 by 2 into RV, about 3 into 461.5. It's somewhat more than that. So it comes out to be about 3 into 461.5, about 1384, but actual value is about 1410. Okay, 1410 joules per Kelvin per kg. What about CPV? Just you have to add 461.5, or it will be just 4 RV, and that comes out to be about nearly about 1900 joules per Kelvin per kg. If you take 461.5, I will tell you what is the expression. It's about 1846, but actually it is about 1900. Fine. These are the values of CVV and CPV. Remember this, that week 4, the problem solving session 4th PDF which I have sent, there I have done using diatomic gas, which is wrong. For vapor, it is a triatomic gas, but its degrees of freedom is not equal to that of the degrees of freedom of the triatomic gases. It's about 6. And from there, we can derive that CPV and CVV is this. Now see how we are calculating Cp of M, or the unsaturated air. Now, mass 1 plus W, total mass is this, because unsaturated air consists of moisture plus dry air. Therefore, 1 plus W CPM into dt, you can write also, is equal to 1 CPD into dt plus the moisture CPV into dt. Now dt you can chop out on both sides. Now this becomes CPM dt you chop out, becomes CPD plus W CPV divided by 1 plus W, right? Now I will do very typical kind of derivation thing to simplify this stuff, and apply here 1 plus W to the power minus 1 we can write, and we apply the binomial expansion neglecting higher order terms. Therefore we get CPD plus W CPV into 1 minus W. What does it give? CPD minus CPDW plus WCPV minus W square CPV. This term I neglect because W is very small, as you already know. This kind of assumption we have already taken. Okay. Now from here, if I take out CPD common, therefore it will be 1 minus W plus W CPV by CPD. Now what is CPD? We have already derived. That is true because for dry air it is a diatomic gas. So 1005 joules per Kelvin per kg, and CVD also I am writing, that is about 718. Now CPV by CPD is roughly about 1.9 because 1900 and 1000 almost. So roughly about 1.9. Therefore it will be CPD 1 minus W plus 1.9 W. And this comes out to be CPD is 1 plus 0.9 W. Okay, this is CPM. Therefore, this gamma of unsaturated will be equal to G by CPD 1 plus 0.9 W. Now, if you have here, if you have W equals 0, gamma un becomes equal to gamma T. Why? Because W is 0, G by CPD. Okay. This is what I try to show, and particularly this particular thing. In the week 4 I have done some mistake there, but this is the correct expression. Okay. Similarly, you can derive CPV also. We can easily see that. Okay. The next thing is that the Cape and the Sine derivation. Okay. We can do it, just small amount of time is required, and types of precipitation also I can discuss. Okay. Now for Cape and Sine, we have already seen that how the cloud formation takes place. See, this is suppose the height or the pressure, this is the temperature. Okay, pressure decreases, so pressure increases in the lower side. Now this is suppose the suppose the temperature profile of the environment. This is of typically the dry adiabatic lapse rate for the dry air parcel. Once it is saturated, it moves like this and it cuts again here. Now this is LNB. What is that? Level of neutral buoyancy, or sometimes it is said as equilibrium level, where these things merges. This is your LCL, lifting condensation level. And this is the LFC, level of free convection, above which the parcel can go on its own because of the latent heat which is there. Okay, now parcel needs to come to this lifting condensation level so that it becomes saturated, because initially the parcel is very much dry or unsaturated. For that, it has temperature, it will have temperature always less than the gamma E, because gamma is typical temperature is about 6.5 degrees Celsius per kilometer. It can vary, but more or less like that. But as we have discussed, the gamma unsaturated, it, see, W is very small, so ultimately it will not vary much. So it will be 9.7 to 9.8 like that way. Okay, so it will be always unsaturated air parcel or dry adiabatic parcel will always have lapse rate greater than this. So stable condition, but we have to lift in order to form cloud. For lifting, these condensation process, convection processes are discussed in the previous session. So all these, any of these processes can form, which will lift that parcel to the lifting condensation level and then up to level of free convection, where this condensation process will start. Latent heat will be enough here and it will go on its own. So this is the energy which is not required. It already has, the parcel already has, but here the energy has to be given. Work needs to be done from outside. That's why it is negative, called CNE, convective inhibition energy, and this is CAPE, convective available potential energy. Now how to derive this particular thing is our thing. So this is suppose P surface, this is suppose P LCL, this is P LFC, and this is P LNB, level of neutral buoyancy. Okay, just simple derivation. See, this is depends upon this work done, and how this work done can be done by the buoyancy force. So Fp times dz. That's all. This is how it can be done. Okay. Now this will be from, now for CNE, suppose for convective inhibition energy. Inhibition energy. Okay. Now here what will happen? dW will be equal to 0 to LCL FB. Now this FB will be how much, or what it will be? See, FB already we have derived, that is Tp minus Te. You can write virtual temperature also, it's fine, by T, or let us write it, that will be better. Just a minute. Yes, so it will be TVP minus TVE divided by TVE, right, into G into dz. Now what we will do is that dP is equal to minus rho G dz. Fine, and this is for particularly for the environment. Therefore dP by P will be equal to minus R, sorry, G by R d TVE dz. So dP by P dP by P will be equal to G by RD TVE dZ. Fine. So now, just a minute, some network issue. Some network issue is there. So dP by P will be this. Now just put this in this. So what I will get, we just do it quickly. Now dW just do it. Yeah. So dW will be equal to integral of Tp minus Te or Tvp minus Tve divided by Tve, now dP by P, and this is Rd into Tve. Now from where to where we will go? We will start from, or just leave it like this right now. So this Tve can be chopped out. Therefore Tvp minus Tve d log P. Now for Cine, it will be from P surface to P LCL. Right? So this is the expression for Cine. Now what will happen? Now this will depend on the height and things like that. So this is the entire expression for the Cine. Now what is happening is that, see, PLCL is always less than P surface. So that will give a negative sign because of that. But TVP minus TVE in that region, parcels temperature is always less than the environment because of this particular thing. This is parcel, this is environment, so it's always less. Therefore this will also generate some negative sign. Okay, and that's how it will be changed. And actually what happens is that dP is equal to minus rho gz, therefore there will be a minus sign. Okay, and this negative sign can be accommodated as Cine will be equal to PLCL to PS TVP minus TVE into d log P. That's all. Now only Cine will become negative as TVP is always less than TVE there. But for Cape, same expression will be there, but it will be now from P level of neutral buoyancy to P LFC, because it will be from LFC to LNB. Okay, now this will be TVP minus TVE, same expression, d log P. But why is it positive? This is positive because, see this area, this is parcel, this is also parcel, this is environment, this is also environment. Now here TVP is greater than TVE. So these are the two expressions of Cine and Cape. Right? And I will detail discussion I will do of this particular thing, the types of precipitation. So this detailed expression I will show, but here the types of precipitation is shown here, and if you can see that these are rain, sleet, hail and snow. These are the four types of uh, precipitation types, very basic precipitation types, and these four profiles are already shown for each of its formation. So what you can see that for rain, it is first positive, and at upper atmosphere it becomes negative. In the upper atmosphere it becomes negative. After that, there is a sleet where you can find out the negative temperature here. After that, there is an increasing temperature. And for snow, there is a complete decrease because 0 degrees Celsius is there. And for the freezing rain, again it's kind of a similar, but high temperature at the middle level. So these are the four temperature profiles which are required for different types of precipitation. This is for rain, this is sleet, hail and snow. So detailed discussion I will do in the next class, and I will show what are the different types of measuring the precipitation events, and we will discuss about the curvature effect, solute effect, and also discuss the assignment 7. Okay, so I stop here. There's some network issue is also there, but this is the last slide which I have. So I stop now. Keep the patience. Okay, now everything is saved. Stop sharing. Okay, thank you very much. Good night.